Welcome to our next video. In this video, we are going to unpack logistic regression a little bit more and try to kind of understand how we arrive at what we call the Logit function as the link function for modeling a binary response variable, modeling kind of the expected value of y when y is a binary variable. I made a little kind of fix here. I wrote 16 in the slides, but now it's a 17. So hopefully that's doesn't bother anybody. All right, so just kind of a reminder. So if y is a binary variable, it means that it's only going to take the values 0 and 1. And when I say that, by the way, we could have some data where we have a binary variable that has like smoker, non-smoker as labels, right? And those are not zeros and ones. But mathematically, we're going to kind of think of them as zeros and ones for the sake of the modeling, for the sake of graphing, for things like that. So again, it doesn't have to literally be zeros and ones in the data, but like kind of symbolically, we're thinking about them as zeros and ones, as yet, like a yes and no type situation. So as a result, the expected value of y here is going to be represented as a probability between 0 and 1. So given some information, I recognize that not every response is going to be 1 or every response is going to be 0 given some set of predictor values, right? There's still probability, just like if we're trying to predict the likelihood that it rains, different weather conditions might increase or decrease that likelihood. But if I, observe 100 days where I had a certain set of conditions, it may rain on 72 of them and it may not rain on 28 of them, right? So even though each individual day is either going to be rain or no rain, I can kind of label that as a 1 or a 0. I recognize holistically when I'm trying to model that, I'm going to represent the expected value of rain, the expected likelihood of rain, with a probability that kind of represents how often it should rain, my best estimate for what's going to happen. So we use this terminology of p of x, which is really kind of a function where we plug in x and then output an expected value of y. So p of x is going to represent the probability that y equals 1 given x equals this inputted x value. All right, so how do we get to this link function, right? So we talked about how we don't just model p of x, kind of this probability that y equals 1 given x equals x directly with a linear equation, because as we talked about, a linear equation is going to be unbounded and additive, and it's not necessarily sensible to use when I have a bounded response variable where our expected value of y is going to be bounded between 0 and 1. So instead, what I'm going to do is take something called the Logit function, and I'm going to take and I'm going to kind of unpack how we get here first. So first, we have this thing called the odds. So the odds of something happening are represented as the probability of it happening divided by the probability that it doesn't happen. So that's kind of a probabilistic term. The odds that y equals 1 will be represented as the probability that y equals 1 divided by the probability that y equals 0. And so the reason I might do this is because the odds is not going to be bounded between 0 and 1. Instead, the odds is going to actually be bounded between 0 and infinity now. That 1 is going to represent equal odds. So a probability of 50% would then produce 0.5 divided by 0.5, and that would be an odds of 1. So if the odds are 1, it means that they're 50-50. If the probability of something happening is less than 50%, then now I'm going to have a fraction that produces a value that's less than 1, but still above 0. So let's say the probability is 25%. Well, now the odds are going to be 0.25 divided by 0.75, and that would give me an odds of 0.333, meaning that the odds are 1 to 3 that this is going to take place. If the probability is above 50%, then I'm going to get an odds value that's above 1. And the thing is, the odds value is technically not bounded from the positive side. It could go up to positive infinity, because if the probability is, say, 99%, then I'm going to have 0.99 over 0.01, which is going to be an odds of 99. So the odds function here is going to be bounded only between 0 and infinity. However, this distribution is going to be exponential. It's not going to be kind of symmetric. And so what I want to do next is take the log of the odds, because the log will actually now scale the odds back to a normally distributed unbounded variable, where the log of the odds should be centered at 0 and normally distributed in either direction without a bounding. And so as a result, it's very easy to model the log odds of a binary event, the log odds of something happening with a linear equation. So we can kind of look at this visually as well, right? So if I'm kind of thinking about probabilities, probabilities are going to be bounded between 0 and 1. So if I just kind of randomly select a distribution of probabilities that could happen, so this is kind of a collection of different expected value of y given x that I could possibly see, and I just kind of uniformly distributed it between 0 and 1. So this is a bounded variable, and so if I wanted to model this with a linear equation, that would be difficult because it's bounded. Now if I turn this into the odds, so if I take these probabilities and then instead calculate the odds using probability over 1 minus probability, I get a distribution that now looks like this, where most of my odds are going to be quite low. They're going to be around 1 or between 0 and 1 or just above 1. And then I'm going to kind of have this skewed distribution of odds where I can get some really, really high odds as well. So this is going to be a highly exponential distribution. But then if I take the log of this distribution, now it's actually going to turn into a normally distributed variable centered at 0 and extending out in either direction without a bounding. And this is a distribution, so the log odds is a distribution that I can very easily model with a linear equation. So if I kind of compare these models, I guess we already kind of did this in the last video, I can kind of see how the log odds just makes a lot more sense as a modeling choice than just a linear equation to try to fit that probability. So this just makes sense and is naturally going to be bounded between 0 and 1 when I make that link function conversion there. Now, while the linear equation is kind of helpful for fitting the model to begin with, really what I'm most interested in is directly finding this probability. I want to know what is the probability that y equals 1 given some input for the predictors. So what I'm going to do is take the inverse of the Logit function. So the Logit function is the log of some value divided by 1 minus that value. So it's the log of the odds of a probability. So if I take the inverse of the Logit from either side, then I'm going to be left with this value, which is going to be a probability. The probability that y equals 1 is going to equal e to the expression on the other side divided by 1 plus e to the expression on the other side. I could also write it like this. Either of these forms is equivalent as the inverse Logit function. And this symbol here, I'm kind of blinking. I want to say this is eta, though I could be wrong. I don't know my Greek letters as well as I should. I'll just say it's eta. This eta here in the context of logistic regression is just going to be my linear equation. So if the other side of my equation equals, I still have the really large font there. Let me switch over to, so let's say that my linear equation on the other side looks like this. Well, then the inverse Logit is going to be p of x equals e to the linear equation plus over 1 plus e to the linear equation. Or I guess I should call it an expression because it's just one side. So an expression is one side an equation is both sides. So it's going to equal this linear expression. So therefore, I can kind of see that represented here as well, that the probability that y equals 1 given x is some set of predictor values is going to be equivalent to this expression right here, where this is the fitted linear model that I created, that I set equivalent to the log odds function here. All right, so interpreting coefficients in this context is really confusing, because if I start from this expression or this equation right here, I might be trying to think, okay, well, what does 3.7 represent if that is kind of the fitted equation that I have come up with? So with ordinary least squares, we call this a slope coefficient because it represents kind of the additive change in y given a 1 unit increase in x. And in some sense, that's still true. It's just that instead of it being the change in the response, it's now going to be the change in the log odds that y equals 1. So as I'm going to kind of interpret this as it is right here, for every 1 unit increase in x, we expect the log odds that y equals 1 to increase by 3.7. And I don't know about you, but thinking about the log odds as a meaningful value is not very easy to me. But that is literally what that coefficient would represent, just so that we kind of have some reference. But it's not like a particularly meaningful value contextually because it's kind of wrapped up in the Logit function, which is not a particularly meaningful result other than just something that makes this equation work. Instead, what we're really going to be focused on is just directly calculating these probabilities by kind of taking the inverse Logit function, so that now we can kind of directly input values for x and calculate our expected value of y, kind of our probability that y would equal 1 in this context. So if we kind of solve this mathematically, we would just use one of these expressions. We could either use the e divided by 1 plus e, or we could do the 1 over 1 plus e to the negative linear expression as well. And in each of these cases, this is the value that I would be getting. More realistically, I'd just be using software. So again, we could just use the predict function like we have before, where we would just fit our GLM model that we've created, that we would plug in the single or multiple predictor values that we want to plug in. And then there's going to be this type equals response argument that I need to make at the end. And so the reason that I have this is because I also have the option of writing type equals link. Because if I were to do this, if I were to write type equals link, what I would instead get is the predicted log odds value. But type equals response will directly take me to the predicted probability that y equals 1, right? So type equals link is if I don't take the inverse Logit function. Type equals response is if I have already taken the inverse Logit function. So just kind of a small thing to keep in mind there. You can also use polynomial terms in logistic regression as well, so we're not going to explore this very far in this class, other than just kind of mentioning that this possibility exists. That let's say that you actually have a model that looks something like this, where maybe the likelihood that y equals 1 is actually changing direction as x increases. So it's not just kind of a steady change in the likelihood increasing or decreasing, but instead maybe it's actually kind of switching directions where it's more likely equal to 0 here, more likely equal to 1 over here. So in that case, it might be appropriate then to fit a polynomial expression for our linear equation as well. And that's actually it for this video.